Okay, so good evening, everybody. And has there been any questions, any doubts? Okay, has there been any questions? Um, okay, I can now give a brief overview of what I have covered in 20 lectures. Let me start the screen. Okay. Okay, so this would be just a brief overview of what I have covered in my 20 lectures. As I have said at the very beginning, this is a brief overview of bioinorganic chemistry. And this is Professor S. P. Rath from Department of Chemistry at IIT-Kanpur. Now, bioinorganic chemistry actually bridges between inorganic chemistry and biology. So basically, the inorganic chemistry in biology, we can say like that. And it is a interdisciplinary field comprising of inorganic chemistry, biochemistry, microbiology, physics, toxicology, pharmacology, physiology, nanotechnology, and all these things are involved in this bioinorganic chemistry. And the main avenues of study is the understanding the role of naturally occurring inorganic elements in biology. We try to understand the structure and function of metalloproteins and role of metal ions therein. We then correlate with their practical applications and the use of inorganic molecules as probes and drug. So there are many such examples like cisplatin, aronophil as pharmaceuticals, gadolinium as imaging agents, etc. Now this is the periodic table. All of you know, but only few elements have been selected for the job we have in biology. And we try to understand that why these few elements are selected where rest of these elements are not selected. Now, what are the selection criteria utilized? And there are many selection criteria that have been utilized. For example, like their abundance in the earth crust and ocean, their basic fitness, efficiency, their evolutionary adaptation to realize critically required specificity and solubility under physiological conditions. For example, lighter elements are more abundant, therefore utilized more. Insolubility of naturally occurring oxides, although they are highly abundant, they are not being utilized in biology. Nature indeed uses relatively abundant kinetically labile and thermodynamically stable units in metalloprotein active centers. So some of these enzymes and proteins I have already discussed in my lecture. For example, hemoglobin utilized in oxygen transport and storage. Myoglobin is indeed oxygen storage. And cytochrome P450 have been utilized for the metabolism of drug and steroids, and cytochrome C oxidase electron transport. So we have discussed in details about these enzymatic systems. Then in the next week, I discuss about the design principle that is used in chemical biology and some of these noteworthy examples. Very exciting examples are there. For example, blue copper proteins, it's an electron transfer protein, and the rate of electron transfer is very, very fast. And we try to understand that why it is so fast. It has been found that the active site of the structure is a copper containing enzymes in highly distorted tetrahedral structure, both in the oxidized and reduced state. So, and this is we call it as enteric state, and that's the reason why electron transfer is so fast. So we discuss in great details about this electron transfer. Like this is what is the transition state, and enteric state is the close to the transition state. Here is the definition: closer to a transition state, that to a conventional stable molecules. Okay, and that's the reason why electron transfer is so fast. So it can come to this site or that site. So activation energies required is very small. Okay. I have then discussed about the nitrogen gas. It is very inert, as you all know. And although it is a kinetically stable, a thermodynamically stable, but kinetically highly inert. And how one can overcome that kinetic inertness. And then it has been discussed that highly reactive, high energetic intermediates can easily be can go down. The energy can go down by utilizing metal ions, and that's what nature has done it. You can see that all these high energy intermediates are getting stabilized in the presence of metal. And this nitrogen is very important because it converts to ammonia, and which is converted to urea. We all use urea in fertilizers as a fertilizers. And this Haber-Bosch process, they do this, convert this nitrogen to ammonia, but it requires very high, more than 200 atmospheric pressure and 450 degrees centigrade temperature. Okay, and that yield is only a 15% conversion rate. So the cost of this production become very high. In contrast, in biology, this nitrogenase, they do the same job with 100% efficiency and at room temperature and normal atmospheric pressures. And in nitrogenase, they use this iron molybdenum cluster. And as I have said, that iron and molybdenum cluster, iron and molybdenum catalyst is being utilized in Haber-Bosch process. So this is a wonder reactions which is happening at room temperature and normal atmospheric pressure in biology. Okay, and we try to understand this process, and then we try to implement at least, so that we can get ammonia easily. So cost would be reduced, and it would be then convert to fertilizers, urea and nitrogenase, nitrogen containing fertilizers. Then I discussed in third week, I discussed about that life with oxygen. And as you can see that oxygen is around 20.9% in air. In the earth crust also it is highly abundant. And nature has utilized this oxygen in our day-to-day life. For example, you all know that this hemoglobin and carrying dioxygen, and dioxygen, this is hemoglobin iron 2 center becoming iron 3 and O2 minus, and then it goes back to iron 2 by releasing oxygen. So this is the transport of oxygen happening. and by hemoglobin, and myoglobin stores the oxygen. And this oxygen is actually responsible for all sorts all sorts of energy that we utilized in our day-to-day lives. So this is the respiration where oxygen is converted to water and produce lot of energy, and it uses 4 proton and 4 electrons. Okay. But incomplete reduction can also produce like superoxide and peroxide, O2 minus and O2 2 minus, or hydroxyl radical, and which are actually called reactive oxygen species. They are indeed called biological poisons and responsible for aging and age-related diseases in our life. Like some of these age-related diseases you can see, and one can easily get rid of these age-related diseases by using antioxidants, and you can take these antioxidants and you can get rid of these age-related diseases. Indeed, a very homemade people use this as a technique to get rid of this reactive oxygen species at home, and you can you can looks like a teenagers by doing that. Now nature has utilized this undesired highly reactive intermediate to useful products. There are several enzymatic systems which are there: catalase, peroxidase, chloroperoxidase, lignin peroxidase, cytochrome C peroxidase. They actually convert these undesired intermediates into useful products. Okay, we have discussed extensively about this enzymatic system. And indeed, there is an enzyme called cytochrome P450, which actually responsible for the oxidative metabolism of drugs, steroids, and carcinogens. And you can see that water insoluble drugs becomes water soluble, and then it get it off from our body. Okay, so it is also taking part of the body detoxification system. And we have learned from enzyme one of the key success story I'll be telling here. It already been discussed in my lecture, but I will be highlighting here today that this is the catalase and peroxidase. So one of our good friend Terry Collins has designed a Tamil catalyst looking inspiration from catalase and peroxidase. They are looking very similar and they do the similar job also. So reactive catalyst or active catalyst are very similar. It is iron 4 oxo picaton radical, and this become iron 5 oxo, and they do the same job. And this has been utilized, one of the very successful oxidants. Now, this is what is happening. This, as I discussed, this iron 2 converts to iron 3 after coordination of oxygen, and iron 3, once it releases dioxygen, it converts to iron 2. Okay, so this is happening, that iron 2 become iron 3 and iron 3 become iron 2 after release of oxygen. Okay. Now, dioxin binding slowly causes irreversible oxidation of iron 2 to iron 3. And once it forms iron 3, it cannot bind dioxin anymore. So overall efficiency of hemoglobin decreases over time. So what is the nature selection? Nature utilize an enzyme called hemoxygenase enzyme, which can decompose this blood and make it fresh blood. And during this decomposition, you can see that bilirubin is produced, and this bilirubin it excretes through our body through the urine. So I have also discussed this enzymatic system, and this is happening all the time in our body. Okay, but if you have a disbalance, you can have then this jaundice, which bilirubin is actually actually yellow in color, and this causes a jaundice. Yeah. We also have discussed in details in my last week that how one can utilize this inorganic molecule for medicinal purpose. Indeed, we discussed the symptoms of elements that are in deficiency. Okay, these are the elements: calcium, magnesium, irons. These are all essential elements, and if we do not have sufficient amount of this element, it creates a lot of diseases. And so the effect of this disease, you can see here, there are a lot of problems one can have. And if you go to the doctor will prescribe a lot of medicines where you are asked to take this metal, like say for example iron tablets, okay, and like calcium tablets, and there are many other things you are asked to do it. And so these inorganic molecules can actually be used as a medicine, metallo drugs, and I have discussed about one such drugs in details, like cisplatin, which is used as a chemotherapy drug and against the cancerous cell. And also there are several inorganic molecules such as gadolinium complex active in the market as a MRI contrast agent. And you can see that these contrast agents are extensively utilized for imaging purpose in MRI. And one can see very clearly that after addition of this imaging agent, one can detect the tumor very clearly. So lots of new drugs and new possibilities are there in this inorganic chemistry for metals in medicines. There is much research to be done, and let us go back to the laboratory. So, in summary, I discussed the usefulness of bioinorganic chemistry in our day-to-day life, starting from these metals in biology. Then I emphasize on the design principle that is being used in chemical biology. Then I discussed about this oxygen, which is highly abundant in our environment, how we utilize this aerial oxygen in our day-to-day life. And then we discussed about the metals in medicines um, as a drug. And I hope that you would be enjoying my lectures, and I will be very happy if you have questions, comments, and please ask your questions. And you can also send email to me so that I can answer some of your query that you might have. Thank you very much. Now, anybody have any questions? Okay, so there is one question is that cooperative effect of hemoglobin. Okay, okay, so it's a good question. Let me look into it. Mm, okay, I guess this is. Okay, so let me share it. Okay, so this is hemoglobin, which is tetrameric unit, and this is myoglobin, which is monomeric unit. And as you can see in my lecture, that dioxin actually binds to oxygen, and iron 2 becomes iron 3, and O2 becomes O2 minus. So metal is getting oxidized by one electron, and dioxin is getting reduced by one electron. Okay, this is one thing is happening. Another thing also happening, that iron in 5-coordinate species is above the mean plane. Now after dioxin binding, this iron center is coming at the plane of the porphyrin. Okay, and you can see that this is 5-coordinate deoxy myoglobin, and once it binds dioxygen, and the dioxin binds in a angular situation, and I remove this protein, and so you see angular binding of dioxygen, and this is what is the um, hemoglobin. And when it binds to the dioxygen, you can see that this is dioxin is bound in an angular position. So this dioxin binding is even facilitated by forming an hydrogen bonding with the distal histidine. Now, coming back to this, so there is a lot of structural changes happen once dioxin binds to iron center. For example, this deoxymyoglobin or hemoglobin is the same, because myoglobin is a monomeric unit, hemoglobin is a tetramer. Okay. Now, iron center is around 0.45 angstrom above the plane. Now, after dioxin binding, this iron center becomes on the plane of the porphyrin. Okay, and this is also connected with a huge protein change. So there is a huge structural change after dioxin binding. And this is the, like this, I can show you, there is a huge structural change is happening on dioxin binding. So iron is above the plane and then coming to the plane of the porphyrin once it binds to the dioxin. So it is happening like that. And because of that, it generates a cooperativity. You can see that. So in general, for any metal complex, if you can prepare, so if the first ligand comes to the metal, it comes very fast. It binds very, binding constant, or formation constant is very high. Now, second ligand comes, formation constant also high but lesser. So then the first one. So basically, this is what happening, that K1 is greater than the K2, K2 is greater than the K3 and K4. This is what is expected. But what exactly happening in reality, what is exactly happening, the K4 is much greater than the K3, which is greater than the K2 and then K1. This is because of the cooperative binding. Okay, so no such cooperativity was, however, observed in myoglobin because of the monomeric nature. So what is happening, that there are 4 units in the hemoglobin. Now in one, when dioxin binds, so then there is a huge structural change around this periphery of the heme unit. and that actually influence the nearby the other heme units. Okay, so there is a cooperativity. They cooperate with each other. So binding of oxygen becoming easier, and this is what is being reflected here. Okay, and so you can see that the dioxin binding becoming easier and easier once dioxin binds it, which is unusual. Okay, and and that's the reason why there is a differential binding between hemoglobin and myoglobin. Hmm. Okay, so hemoglobin, the dioxin binding saturation curve is like this for hemoglobin, and for myoglobin like this. So what does it mean? It means that dioxin binding is, so this means that at lower oxygen concentration, myoglobin is fully saturated. But hemoglobin will be saturated at higher oxygen concentration, which is present in artery. Myoglobin is saturated around at this in the venous oxygen concentration, where oxygen concentration is very low. Okay, this difference is coming because of the cooperativity. I hope you understand. Any other questions? Okay, so no other questions. Okay. One can also send email to me. I can respond to that also if they have any query. Um, the lecture, I think what document is already there. PDF copy. PDF copy of my lectures are already there. Okay, so let me wish all the best for your exam. Thank you. See you again.